Hey everyone, long time, no devlog. I've been making things this whole time, just haven't really had the motivation to record myself talking about the things I make because I didn't think I had much interesting to say. But I came across a topic when working on a jam this month. I'm doing the Secret Santa game jam. It is a 2 week jam in December. Everyone writes a letter to Santa, and then every group gets a letter from Santa that they then must make a game based on that person who wrote them the letter, right? So you write about yourself, what you like, but you don't say specifically, I want this game, and then you then get a game made for you custom by some person, and you make a game custom for some other person. And so I wanted to have a bit of fun, and I wanted to hard force a mechanic in my jam game. That mechanic, if you couldn't guess, is going to be using a hex grid, right? So lots of games that I've played in my life use hex grids, old and new. The oldest game I can remember using this was a game I used to play on my computer in like math class. It was called Trap the Cat, a game where you trap a cat. Um, it is a small hex grid. You can block one hex. The cat can move one hex every turn, and then you either lose when it escapes, which it's actually harder than you'd imagine, or win when you block all of its possible moves. Um, and so that's like the earliest I can remember using it. There are modern games that I like too. Ones like Nordhold, which are a 3D hex grid, like what I'm making here. And those 3D ones. This is like a tower defense. You can place things upon hexes, and then units will run in, siege you, and you either built a good enough city to resist that, or you didn't, right? And so lots of games use this mechanic, so it's already been solved before. But being myself, I like to reinvent things to truly understand how they work and make a worse version of what exists out there. I mean, even Unity has tooling for this, but it's a 2D hex tile map, which is not exactly applicable to 3D. So I've been reinventing this wheel myself, right? And I've been having a lot of fun doing it. And I came across um, some interesting knowledge that I thought would be fun to share. So when reinventing this wheel, I realized there were three problems to solve, right? The first problem is in a repeating hex grid, right? Um, how do I define movement, right? I'll get into why this is an interesting problem uh, later. But how do I define movement, right? What is from a point in space? Well, it seems like there's six possible things to move to. So it can't just be like 1, 1, right? Or 1, -1, or just 0, 1. You can't exactly do that, right? That wouldn't work. And the other two problems are sort of the same problem forward and in reverse, which is how do you know, given a world space coordinate, what hex you're in? So if you are the base of this tree trunk here, what hex coordinate is that tree trunk in based on its the bottom of its trunk, right? And so you have to do some math there. And then the reverse problem is, well, where is a hex coordinate in world space? So it's just two conversions. They're like the same thing forward and backwards, right? So I wanted to solve some of those problems. And so the first problem, let's take a look at that one. So we're going to dive into a different type of game really quickly, like Sokoban, for example. If you know Sokoban, Sokoban is a block pushing game that takes place on a tile grid, not a hex tile grid, but a tile grid of squares. And you push squares in that tile grid to either get them in the right position or not. And there's lots of variations on Sokoban games, but that is the main formula. And in any Sokoban or just square grid tile game, you are solving a really, really simple problem, right? So if you have this is your grid, right? Let's draw like 3 lines, 2 lines. Yeah, that's probably fine. If you wanted to move from here to here, for example, we'll draw a fourth line. If you are in the XY coordinate space, right, that is simply 1, 2, 3. So 2x, 1y. That is the movement you're doing. That's a very simple movement to define. Even if you were doing a cube map, 3D movement makes it no more difficult. You add a z-axis. Okay, well, for this movement, it was 0, right? That's a simple problem to solve. It is easy to define movements on a square grid. Not so easy for hex coordinates. So let's go ahead and take a look at this little pre-drawn example I have here of hex coordinates, right? So this is a basic I guess you'd call it a 2 by 2 because there's two distance, right? But if we are here, this is 0, 0, and we want to move to the center of this hex coordinate, well, what is this distance? I don't know. In XY, I mean, you know a few things about hexagons. A regular hexagon, for example, of side length L. All side lengths in a regular hexagon are L. And conveniently, that means all the triangles are equilateral. So all three of these are L, L, right? And so that means you are moving L distance, which means, I guess, this straightaway here, since it's an isosceles with two side lengths L, is square root of 3 times L. That is the distance, right? Very convenient. So, and that's not how you solve for that, but that's just the answer. So we need a new coordinate system. Well, what coordinate systems are there? Well, we can't use x, y, or x, y, z. So the only other one that I've learned in my life, and so you probably have learned too, is polar coordinates, right? So if you're given a polar coordinate, if this is 0, 0 in polar coordinate, the first movement would be theta and r, right? And you can repeatedly chain these to get movements in any sort of system. And you could probably use that since all of these, are, what is it, 6, so 30 degrees apart. I guess you could probably easily define that. But, oh no, I guess it'd be 60. Yeah, 60 degrees apart. So it's like, you could maybe do it that way, but it's not exactly easy to understand what a movement is in polar coordinate, right? Like you have to, there's a lot more work there. So we're going to make up our own coordinate system. So let's just see how we would do that, right? So we have 6 movements we want to accomplish. We want to move to each of these 6 nodes. Okay, so how many axes does our coordinate system need? Well, let's just start. Let's move to here. Okay, well, that's one axis for sure. Well, since we have a movement of 1 in that axis, what does -1 look like? Okay, gets us here, -1. We have a new axis that we want to do. Okay, well, here's the 1, and here's the -1. And then similarly, we have a 1 and a -1. Actually, we're going to call this 1 and this -1. Okay, that's really nice, right? We have 3 axes, right? We have, let's name them, Q, R, and S. These are not my original names. Someone who solved this problem a long time ago came up with these coordinates names, Q, R, and S, not me. But we have Q, R, and S. Okay, so what movements do we have available? If we were going to stop here and make this our hex coordinate system, okay, where do we stop? Okay, so we have 6 movements available. We have 1, 0, 0, -1, 0, 0, 0, 1, 0, 0, -1, 0, comma there, and then 0, 0, 1, 0, 0, -1. And so there are some equivalencies we're going to make here. Is we are going to set a constraint, right? To say that this 3 coordinate system is representing 2 coordinate space. So we can say a few things. We know that Q plus R plus S equal to 0. And this is an important constraint to set. And it allows us to do certain equivalencies. Like, for example, we know that S is equal to -Q minus R. That's actually really useful information because that allows us to simplify our possible movements in our coordinate system, right? We no longer have to store 3 coordinates or 3 axes of information, just 2, because we can always infer what the third axis is from the other 2. Okay, well, what does that make our movements? Well, we still want to be able to move 1 and -1 on Q. We still want to be able to move 1 and -1 on R. Okay, all fine and dandy. But now, and this is a fun inference to be able to make, how do we get to these S positions? Well, it's really not that complicated. Let me first not write down. So we have 1, 0, -1, 0, and then 0, 1, 0, -1. You could do math to prove this, by the way. there is math that allows you to solve for this by getting all 6 possible answers to this equation, using this to solve and replace. Even simpler than that, though, let's just imagine how one would get to 1 here on the S coordinate. Okay, well, we can move 1 to Q and -1R from there. Okay, so the movement is 1, -1. Right, because to get to here from the center coordinate, we have to move 1, 0. To get from here to there, it's 0, -1, 1, -1. And the same applies to getting to here. Let's say we move -1Q, 1R. Oh, wow, we have 6 movements defined, and it didn't even take any math. It just took a little bit of basic understanding of how you would move. And so let's do a little bit of a harder puzzle here, right, to maybe nail it in. So if we wanted to move to here, right? We wanted to move to this hex all the way out here. That's 2 in the -S direction. Oh, tough, right? Is it really, though? So we need to move this twice. Well, conveniently, you could just go ×2, right? But we'll imagine it anyways. So we can go -2Q, 2R to get there, right? So -2, 2. If you wanted to get somewhere even more complicated, the same logic applies. You can always ascribe it to those 2 coordinates. And so that solves our very first problem, right? Because what is there left to know? I don't think there's much, right? At least in terms of how to describe movements, you can easily describe any movement in any direction in terms of what coordinate you're at. But now we need to be able to solve the coordinates of things, right? That's the other 2 problems. How do you know what coordinate you're in? How do you know where a coordinate should be? And these 2 problems solve each other. You solve one, you solve the other one. But if we go back to the very first detail I told you about hex grids, which is the whole side length thing, side length of L, and that this distance here is square root of 3 times L. Let's say that we have a point that is right here, right? Well, in the Q direction, which is, I guess, we could align the XY grid like this, right? X, Y, X, Y. Well, in the X direction, that is greater than 1 of this distance. So I guess we could say X is greater than, but less than 2L. Okay, so we know that its Q is going to be 1Q. And similarly, in the R direction, we know that it seems to be, it's a little less than 1, right? So that's the approximation you're going to do, and you do some rounding work. But I'm not going to redo all the math because it's a little ugly, and I don't feel like writing it out. But I'll show you the code of what that looks like, and then I'll show you a demo of what this really basic math setup gets you to do, right? So here's my hex coord class, hex coordinates. You could name it something more serious, but you'll notice that it has the Q and the R. That's all it has, a constructor, a helper method, and some operators that let me easily print and stuff, right? Nothing really that crazy, very simple class. And then here's the hex grid. This is never going to change. It'll always be 1, but it is there. The hex radius being the edge length, being the distance from the vertex to the center of any hex, right? It's not actually a radius, but it's kind of close enough if you ascribe a circle to that point. And then I have a bunch of pre-computed things here. You don't have to pre-compute as aggressively as I did. I just do that because these functions run so often, sometimes every frame. And so, like, I don't want to be recomputing what the square root of 3 is every frame. That's slow as fuck. And so I even pre-compute some of the divisions and multiplications. It's just, like, very marginally faster. I'm probably squeezing performance. It doesn't matter to here. So we look at this equation here. If you recall, the way I drew it, you have the x-axis is here. So we know that both Q and R run in the x-axis. And so the math is a bit approximate, but you have half of the distance in R is half of the distance in X and half the distance in Y, because we're moving in both axes, right? This is adjusted per the angle. And the same problem is being solved here, where you have you're converting the world space axis to the Q and R space axis using that distance between points that we discovered. And then we're doing some rounding math. The rounding math is simply to say how far off of that center of the coordinate are we, and we need to adjust then the coordinate to be at that center, right? And so we're rounding everything down to integers because we're only moving coordinates in movements of 1, right? So we're rounding everything down to the integer, and then we're saying, okay, well now based on that equality, right, of q plus r plus s, which we solve for s here, as you can see, yf, how far off that equality are we? And then based on whichever distance is furthest off, we're going to reset that back to the equality we want to see. And then bam, we have a world space to coordinate, or coordinate to world space, whichever way you want to run it. The math is a little complicated. I could write it out, but it would probably take longer than it's worth. The point is you can look at this and see it or find some information. I'll probably link below the video where I learned this stuff. Obviously, I'm still kind of learning it. This is newish information to me, but it was fun to learn. I hope you learned something. If you didn't, I hope you learned to want to learn something and then go make it yourself. Do it better than I did. Who knows? And then you can have a cool little product like this. And I'll show you sort of what I have going here, which is not much, mind you, but I have obviously using this. If we turn on my my gizmos here, I have a bunch of graphs, right? This is a walkable graph for agents. So if I spawn an agent and tell it to walk over here, you can see it moving like a little board piece as it travels across the world, spawn a few of them. And you can see just with a little bit of math, I have these agents hopping between their hexes, going to their destination hex. And that will be the bulk of the game, just moving things around the little hex grid in a little puzzle-like way, I imagine. Not sure entirely yet, but I thought that learning about coordinates and hexes was cool. I think if you make a game yourself using these ideas, you should probably maybe make it yourself and learn something for fun rather than just using tools given to you. I mean, maybe if you're going to make something like for money, probably just use the best things available to you. But if you're doing it for fun, have fun making it from scratch if you want, if that's something you enjoy. If not, then, well, just download things. It's fine too. Whatever's the most fun for you. But I like recreating the wheel. I hope you do too. Hope you learned something. If not, hope you yearn to. Anyways, bye-bye. Thanks for tuning in if you did.